Well, did you guys have dreams about falling hydrometers and all that good stuff last night? That lab was epic, wasn't it? It's one of the best ones we do. It's actually not the best, though. That's yet to come, so stay tuned. I'm having a little bit of I don't know, I'm having a little bit of indecision on what to do today, and maybe you guys can help me answer the question. A couple of options. So lecture 6 is like super short. I think it'll take 12 minutes. We have the option of doing 6 and 7 today, just jamming it all into one fell swoop, and then not having class tomorrow. The other option is we can do a shorty today and another kind of shorty tomorrow. In either case, there's going to be an assignment due. I'm going to have you make another calculator. So what would you guys rather do? Let's see. There's a way to react here. So if you want to chug 2 lectures out in one day, how about you raise your hand and I'll count. Okay, I saw 3 physical hands go up. And who would rather split it up? Okay, I don't see anybody voting, so let's do them both today. How's that? And then for tomorrow, we'll have an assignment to do. And I apologize, it's going to be another Excel calculator, but it's going to be easier, I think. I think it'll be a little bit easier for you. Okay, let's get started here. Let me swap screens here. Can all see that okay? How are we looking, Garrett? Good? Okay. All right, so let's start talking about soil structure. I think this is something that you guys have probably seen already. At least in the slides of this class, we've maybe pointed it out a few times, but maybe not given names to it. So really what we're talking about is how the different forms in the soil organize themselves. And there's a few things that drive this. The biggest one is clay particles. Organic matter can be a driver, and then chemistry as well. And I'll kind of show you some examples as we go along. But clay is probably the biggest driver in how these units will form into themselves. And when I say units, this is what I'm talking about. So in the soil, we can have a granular structure where we get these nice, not too big, but not too large PEDs. This is what we call granular. If they start forming themselves into something quite a bit bigger, that's when we move to blocky. Prismatic is you get these prism-shaped vertical structures. And you'll notice that the columnar kind of looks similar, right? What distinguishes prismatic from columnar is that prismatic usually manifests itself in subsoil, where you'll get a columnar formation most often towards the soil surface. Okay, and this last one is platy. And that goes without description. I don't need to describe that to you, right? It's just layer on layer stacked on each other. There's one that's not listed here that is kind of important, especially around here, and that is something that we call massive. Okay. A massive soil structure is where it usually ends up that we have just sand. And so the sand is unable to form itself into a granular or a blocky structure. Of course, it's not going to be platy or any of these others. It's just kind of a big fat mass. And that's what we call a massive structure. Okay. Don't pay attention too much to this slide right here. If you were to go out and like field evaluate this stuff, these are some size classes that you might break things up into. So basically, there's 5 size classes, 1, 2, 3, 4, 5. And, if we're talking platy, anything that's less than a 1, we're going to size into class 1. If it's bigger than 10 millimeters, we're going to size it into class 5. So, like I said, don't really worry about this too much. You'll notice that the blocky stuff is pretty big, so 50 millimeters, and the prismatic and columnar stuff is pretty big as well. But I don't even know this stuff, to tell you guys the truth, so I don't expect you to either. But there are different like size classifications for prismatic, for blocky, for platy. Okay, this is a perfect example of a granular type structure. So if we're looking at a soil column and we get these nice, smallish, these aren't blocky because they tend to be pretty small. They're like, I don't know, the size of the tip of an eraser, maybe a little bit bigger than that, and maybe even a little bit. For scale size, you can see these aren't very big pieces. This is what we call a granular structure. Okay, without looking, what's this one? Rod, what do you think?
Platy?
Platy.
Platy. There you go.
Yep. Yep. And here we get this, the horizontal formation. You see it, it's really nice and defined up here. So this would be a platy structure. These tend to have quite a bit of clay in them. And actually, I've seen this before in Washington State. Is anyone in the room from Othello? If you go to Othello and Highway 26 that goes, basically cuts through town, as you head east out of town, there's a pretty big cut on 17 and 26. There's a pretty big cut through the ground there. And if you drop down into kind of that ravine, you can see some nice platy structure. Okay, this is blocky, of course. So, we have basically, this is a granular structure, except in this case, it's much, much bigger. Okay, blocky. This is a prismatic structure. You'll notice that we said before that prismatic and columnar are distinguished because this is subsoil. So this being subsoil right here, we get the nice vertical cracks forming. This is a prismatic structure. This, on the other hand, okay, we're looking at surface soil right here, and it's formed itself into this columnar structure. All right. Now, if we're talking about these and we're talking about water movement, if you guys had to guess, which one of these would cause water to move through it the fastest? What about Lily? What do you think?
Blocky, maybe?
Yeah, yeah, not really. You're close. For the intents and purposes of this class, we're going to say that granular is going to move water through it the fastest. And the reason being is that, these are smaller congregations of sand, silt, and clay right here. And, if you add up all these little bitty pieces of pore space, it's going to be more than the blocky structure. And Joe, which one do you think is going to be the slowest? This one's pretty obvious.
Platy.
Absolutely, it's going to be the platy. So ranking these, we're going to say that this is the fastest, followed by blocky. We probably have a draw between prismatic and columnar. I wouldn't say that one of these is going to be faster than the other. And then this one absolutely is the slowest. Okay. Now let's talk about pores and pore sizes and stuff like that. If we're looking at like a sand grain right here, and depending on how these things organize themselves, so you'll notice in this case, everything's kind of offset equally versus this where it's kind of scrunched in. And this one where it's kind of scrunched in, but we've got these smaller peds in between in the pore spaces right here. all these things are going to affect water movement. It's going to affect water holding capacity. Just keep in mind that pore space is the space between PEDs. If we're gonna call this a PED, we'll call these little guys a PED right here. Now, okay, we need to talk about macropores and micropores. So if we have like a coarse sand particle, we can't cram water into a sand particle. That's impossible. And so in this case, we've got these big void spaces right here. These are called macropores. These are large pores. We can't fit water into these individual sand particles. And so the only water that's going to exist here is in the macropores. Now, if we have aggregations, so in this case, we've got loamy aggregates. So you guys know from yesterday that a loamy aggregate is a certain mixture of sand, silt, and clay, right? In this case, they've kind of coagulated into a PED, okay? And so again, we can have water that lives in these void spaces right here, the big macropores. But now, because there are sand, silt, and clay particles here, there's actually microscopic pores in there as well. And that is what we're going to call the micropores. Does that make sense to everybody? So macropores are these big void spaces right here. Micropores are the little tiny spaces between sand, silt, and clay particles as they live in this kind of aggregate or PED. All right. Here we go again with the water movement. I guess I already talked about this. This is really out of order. So we get rapid movement through the granular structure, moderate with blocky, moderate with prismatic and columnar, and then very slow with the platy structure. That was it for that lecture. Let's go on to lecture number 7. Let me pull it up here. Lecture 7. Let me download this thing so we can look at it. Okay, so let's talk a little bit about these solids and pores, and we'll define density. We did that a little bit yesterday. We've seen this slide before, right? Usually I try to kind of go over this again. So we can't talk about soil pores and soil structure without talking about water too. And a few things. Number one, we need to talk about polarity. We need to talk about hydrogen bonding, and then adhesion and cohesion. Let me pull up a whiteboard here for just a minute. All right, can you see that okay? Can I see a thumbs up from somebody? I think your heads are nodding, but you might be falling asleep. Okay, let's talk about water for a second. We know that water is H2O, right? Everybody knows that. So if we were to draw this thing chemically, it's going to kind of look like this. Okay, and really the way this works is, there's two electrons that are associated with oxygen, and this hydrogen takes one of them, and this hydrogen takes another. But there's also like they call it a dipole moment, and this is like you'll study this in chemistry if you choose to do so. But there's a little bit of a charge that lives here and up here. And the beauty of that is that when we have water, we don't just have one water particle, right? So if we've got kind of a negative charge that hangs out right here, then this hydrogen, not the same one, but another one will come in there and it'll match up with it. And you get water that sticks together. Now, you guys have all seen this before, and I've got some slides coming up here in a bit, but this is what happens. So if we've got a plus hanging out there, we've got this oxygen that wants to match up with it, at least temporarily, and the cycle continues. Okay, this is how water holds itself together. Now let me go. Does this make sense to everybody? We got charges matching up, so that guy's matching up there. These are matching up there. We could have an oxygen that would match up there. Maybe another one right there. Okay, let me clear this off and go back to sharing my other screen. Okay. Through a phenomenon called hydrogen bonding, that's what I just showed you, okay? The hydrogen atom in one molecule is attracted to the oxygen of a neighboring water molecule. And so we end up getting this, it's really a weak bond, but there is kind of an electrostatic bond between the two. And because this happens, we have what we call surface tension. Okay, and let me advance the slide here. Come on. Oh, why did I draw that? I just show you the same thing right here. Okay. When we have water particles that are attracted to other water particles, so here's a water molecule right here, and it's attracted to this guy right here through this hydrogen bond. This is what we call cohesion. Okay, cohesion. Cohesion is the attraction of one that's a mouthful. One water molecule for another water molecule. But we also get a phenomenon called adhesion, okay? And that's when we get attraction of hydrogen for a soil surface or a soil particle. Did I tell you guys that soil particles are charged yesterday? I absolutely did. And do you remember what charge they have usually? Wade, you nodded your head. Tell us.
I think you said they were negative.
Yes. Okay. And so knowing that hydrogen is positively charged, okay, and if a soil particle is negatively charged, there is some bonding that can occur between soil particles and water. That's what we call adhesion. All right. Now, everyone's familiar with cohesion, even if you didn't have a name for it. Let's see, Chris, what's this guy right here?
Like a water fly, water bug.
Yeah, I used to call them water skippers when I was a kid. But these guys can just hang out on the top of the water. And how on earth is that possible? What do you think, Lily?
Through the water particles sticking to them and then on the water.
Yeah, right. So what we're seeing right here is he's really light and his weight is not enough to break the cohesive force of the hydrogen bonding in the water. Okay, pretty cool, right? The same thing happens when we do this with water, right? If you get your fingers wet and pinch them together and then slowly pull them apart, those water molecules will actually stick together as you eventually it'll pull apart. But this is also another reason why when you do a belly flop into a pool, that it hurts like a son of a gun. Because if there was no like hydrogen bonding in the water, you just fall in, right? But since the water particles want to stick together, when we slap into the water, that force of breaking them apart gets moved to our bodies, and that's why it hurts. Okay? Great. Now, in a soil, this is what we call ideal partitioning, okay? And so let's say for a minute that we have a 1 foot, 3-dimensional column of soil. If we were to take that 1 foot of soil and compact it so that we separated the solids from the water, from the air, we typically have about 50% solids. We'll have about 25% water and 25% air. Okay, does that make sense? We squish everything out, and this depends, right? If we're irrigating a field and the circle just passed over the field, we're not going to change the percentage of solids in there. That's going to stay the same, right? But we're going to exchange air for water. And so we might have, 75% water and only 15%. I don't know. Did I do the math right? I think I did. And only 15% of air. So usually there's an exchange for these two, but the solids is the solids. It doesn't really change. Oh yeah, that's what I show with that arrow right there. Great. So there's some forces that are going to affect how water moves based on whether we have micropores or macropores. So in macropores, remember these are the big ones. These are affected by gravity. So gravity is moving water through the soil. We got the air that lives in there as well. So we're swapping air for water or water for air, depending on how much water we put in there. We can also get some really thin films. Okay, let's say that we saturated this coarse sand down here and then drained it all out. There is still going to be a really thin film of water that adheres to these particles. We talked about adhesion, right? Okay. Now in micropores, we talk about something that is capillarity, and I'll show you that in just a moment. But capillarity is where we get water that can actually be sucked into here. Okay. Again, the water is a driver, and we can have air that gets trapped in these itty bitty teeny tiny pores. So those are the forces that affect movement of water in micropores. All right, so let's look at this, some examples here. Now, again, these are solid soil particles right here. And in this case, the black stuff here is water, okay? So we've got our solids shown as this, shaded area down here. And it's full of water, and there might be some itty bitty teeny tiny pores of air in here, but just not very much. So if we add the 3 up, adds up to 100%. We're talking volume, right? So half of the volume is solids, and in this case, about 90% of it's water. On the flip side, if we let the air, or if we let that water drain out, we've got the same 50% solids, but our water's gone almost to nil, and the rest of it's filled up with air. So you can kind of see how the air and the water just kind of exchange with each other there. So that's a dry versus a saturated soil. Saturated meaning practically all of the pores are occupied with water and not with air. Okay, capillarity. So this isn't a great example, but have you guys ever taken a cup of water and then let's say that you rolled up like a paper towel and you stick it in the cup and you can watch water move up? Have you guys seen that happen before? The reason that's happening is because of capillarity. And what's going on in capillarity is two things. The water is being adhered or attracted to the solid. So in the case of the paper towel, it's the paper towel. But also the water particles are attracted to each other as well. So from the forces of adhesion and cohesion, those are causing that water to move up. That doesn't make sense, right? How can water move uphill? That's impossible, right? What do you think, Madison? Is that impossible for water to move up? The correct answer is it is not impossible. It is possible. Okay, I couldn't hear you. Maybe mic issue there. Yeah, still no bueno. I can't hear you. Can anybody else hear Madison? I can't hear you. At any rate, let's go on here. This is a cool way to demonstrate this, okay? So if you have like what we call a capillary rod, okay, this is something that has a really narrow diameter. If you were to stick this into like a pail of water, again, because the water particles are attracted to each other, and they're also attracted to the side of the capillary rod, you can get water that moves up. But as the diameter increases, you'll notice that the rise in the water goes down to next to nothing, okay? This is what we call capillary rise. So it is possible for water to move uphill. And if we were to look at this from like a soil perspective, okay, let's say that we've got sub-irrigation down here, so maybe like a water table. We can get water that moves up because it's attracted to these soil particles and to itself. But because these soil particles are so far apart, it's not going to rise nearly as fast as if we have something that's really fine, okay? There's more surface area here to attract to, and thus the water moves up higher. All right, does that make sense, everyone? Just remember, and I know that there's a quiz and a test question on this, and it says, what direction can water move in soil? And the correct answer is it can move every direction. It can move up, it can move down, it can move sideways, it can move diagonally, it can move any direction that it wants. Okay, so let's talk about density for a little bit. We need to talk about bulk density and particle density. And I want you to write this down. Bulk density is weight, dry weight per volume. Dry weight per volume. And we usually measure this in grams per cubic centimeter. That's what this is right here. And particle density is a given. So write this down. Particle density is a given, and it is 2.65. 2.65 grams per centimeter cube. And I'll show you how to use this stuff in just a little bit. Oh, there it is right there. Particle density, 2.65. What this is based on is the density of quartz. So if you were to go, I don't know, don't do this, but maybe if you Googled the density of quartz, it would tell you it's 2.65 grams per cubic centimeter. Okay, and that's what we're saying, that the solid material in a soil has that bulk density. Bulk density is kind of fun because the threshold for bulk density is 1. Anything that is greater than 1 is going to sink, and anything that's less than 1 is going to float. Okay? So if you were to take like a piece of wood and measure its bulk density, wood floats in water, right? And so you know that its bulk density is going to be less than 1. If you were to do a rock, it's 2.65. It's going to sink. All right. So texture is a big player in bulk density. As we said yesterday, which weighs more, a bucket of sand or a bucket of clay? Who haven't I picked on yet? Mackenzie?
What did you say? Which is more dense?
I said, which weighs more, a bucket of sand or a bucket of clay?
Wouldn't it be a bucket of sand?
Yes, you're exactly right. Okay. And so you can see just that texture is a player in how much something weighs. So we're talking about bulk density. Soil structure is important too, right? if we have a platy structure versus a granular. Joe, which one of those do you think has a higher bulk density, a platy structure or a granular structure?
Granular.
Anyone want to try again?
A platy.
Yeah, you only had one other choice, right? Okay, yeah, because those plates form on top of themselves and really they're really tight. Okay, we're cramming a lot of soil into a smaller area, whereas a granular structure, you know, you've got those nice big macropores and airspace, and so because of that, the bulk density is going to be lower for granular than it is for platy. Most soils are going to be somewhere between 1.15 and 1.65. And the exception being if you have an organic soil, it's usually going to be less than 1. So mineral soils are going to sink, excuse me. These mineral soils are going to sink because they're more than 1. And if we've got a lot of organic matter, that stuff's going to float because the bulk density is less than 1. Okay. We're going to kind of skip this. Let me look around here for a minute. Basically, what I'm going to have you do for your assignment tomorrow is I'm going to have you create a calculator. And in the calculator, I want you to calculate the following things. You might write this down. If not, don't worry. I'll post it on the assignments and it'll all be there. But I'm going to have you calculate percentage of moisture. I'm going to have you calculate bulk density. I'm going to have you calculate pore space. And I think that's it. And it's just easy math, guys. It's super easy. You can cheat and look here and find out everything you need to know. Okay. Yeah, that's it. That's all I've got for today. So I'll post that on the assignments. It'll be super clear. And I'll have you, I don't know, do you guys want to have it due on Friday or Saturday? What's your preference? I don't like to do it on Saturday because I'd like for you guys to have a good weekend and to not have to be doing school crap your entire lives. Okay.
Yeah, Friday works for me.
Okay, how about Friday at midnight?
Perfect.
And yeah, that way you don't feel like you have to get it done on Saturday. Or if you don't do it, then you can feel bad all weekend. I don't care, I guess. Okay. All right. Do you guys have any questions for me? Okay, do this math by hand first, right? Make sure you can do it by hand and then make it work on Excel. And it's going to be easy. You're going to have a space where you're going to put in wet weight, dry weight, and volume. And from that, you can calculate moisture, you can calculate bulk density, and you can calculate pore space. Okay, well, that's all I've got for today. And I'll get that stuff posted for you. Let's see, we're going to meet again on Monday. We don't have another holiday it's next month that we have another holiday, right? So we'll meet on Zoom on Monday. Sound good? And I think we might be getting close to another quiz. So be ready for that. All right. Well, I'm going to shut it off and you guys have a good day, good weekend.
You too.
All right. See you.
Thanks.
See ya.
Bye.